instead of fixing it, I want to kind of just redo it so that there's no ambiguity at all. Do you remember what it was we were talking about yesterday? Can somebody tell me what it was we were talking about yesterday?
Figuring out the frictional force.
That's true. That's good. I sometimes wonder if you guys remember things from day to day. Not because I think less of you, but just that I don't think any more of myself than I think I should. You have 7 such events during the day, perhaps, right? I'm just number 5. And so I would assume that that's a lot to kind of keep track of where you left off in each one of those 7. I know some of you probably only have 5 or 6, but many of you do have 7. Well, some of you have 7. So let's just say that I'm trying to be empathetic to the fact that maybe, just maybe, Mr. Sheldon, you don't always remember. So saying what I just heard, that's good. We're trying to find the frictional force for an object on a ramp that can roll. And you'll find my omission pretty quick because I'm not going to spend a lot of time going through it all. So let's start from the beginning on this, but we'll skip a few steps. So let's draw the arrows first, just to get a reminder of where we were. Tell me an arrow I should draw. Direct me. Okay, so one of those?
Yes.
Excellent. Can somebody tell me another one of those I should draw? All righty. I want to do this one good, so. How is that? Is that all right? And yes? Well, I think that's the intention, since we're going to be looking for the frictional force, that the ball is rolling.
Then friction up the ramp.
Friction up the ramp. Now, this question came up yesterday, but I don't think it was in this class. Does it matter which direction this thing is rolling in order to do this portion of the problem? Do we all understand the question? Because sometimes I fear the question is like you don't understand what I'm asking, but there's 3 possible things that this could be doing at this instant in time, right? It could be on its way up, it could be on its way down, or it could be at the peak of its motion. Correct? Those are the 3 possibilities. Is the acceleration ever any different for any of those possibilities? Do you understand the question I asked? Does it ever have a different acceleration for any of those 3 states that I just named? I'm not trying to trick you at all. Can we agree that the acceleration is slowing it down on the way up, speeding it up on the way down? So acceleration always down the ramp. Agreed? Any of the forces changing during the course of its motion? Any reason to believe the normal force has changed due to the course of its motion? Any reason to believe the weight has changed during the course of its motion? Those are the easy ones. The one that you're concerned about, because it's already kind of been difficult for you, is the frictional one. Because we know that it could change size, right? By definition, its size allows for it to change, right? Static frictional force can be up to, but not to exceed this threshold. It's a reactionary force that provides as much reaction as is necessary for the situation. But I want you to think the frictional force has to oppose the motion of the turning of our spinny object, right? So we know it's got to be up the ramp on the way up the ramp, and we know it's got to be up the ramp on the way down the ramp, because when it's on the way down, it's the frictional force that is helping it, speeding it up, right, on the way down. All those make sense? All those seem reasonable and plausible. So I think this works, whether it's moving up the ramp or down the ramp. Now in this class, if I recall, we were able to break this up into appropriate coordinate systems. I don't think I have to do that part in front of you anymore, do I? So we know that there's a net force down the ramp that's equal to mg sine theta minus friction. And we know that there is a net force into the ramp that is normal force minus mg cosine theta, and that equals 0. All good? So I don't know why I drew a red box. We don't need a red box. So let's just kind of get that out there. If we make the x direction this way, and that's positive, then we get mg sine theta minus friction equals ma. And we can make up the ramp positive too. I don't really care. I don't even remember what we did yesterday. It doesn't matter. But I think the acceleration is down the ramp, so I'm making it the positive direction. That's it. At the same time, we know net force in the y direction equals 0, so normal force equals mg cosine theta. Can't solve this for the frictional force because we don't know the acceleration. That's what it comes down to. So we need to get rid of the acceleration, and that way we can solve for the frictional force. We have choices on how we do that, but one of those choices is to determine where we place our pivot point so we can observe the torque that's acting on the spinny thing. I think in this class we put the pivot point at the point of contact, right? Did I allow you to make that choice?
No.
I chose it for you?
Yeah.
Do you want to make that choice? Because you can. Where's the other place we could put it? We could put it in the middle. That'd be fine. But it doesn't matter to me. So are we good to put it at the point of contact? All right, so we'll put the pivot point here. Now that means that my torque is from the force of gravity. We're saying that this point isn't moving with respect to the surface, which we know that's the definition of rolling. So our torque comes from mg. Why isn't the normal force applying a torque in this circumstance? What's that? Yeah, it's at the pivot point. That also explains why the frictional force isn't applying a torque here too, right? Because we picked the pivot point to be here, so we've eliminated those two forces from providing a torque, but the weight's still providing a torque, isn't it? And I think we can agree that the torque from that weight is going to equal I alpha. Still all good here? Alrighty. I had recommended that perhaps we find the acceleration, and then we could eliminate the acceleration between these two relationships. So let's create a relationship here by putting in our expression for the torque. Torque is torque arm length times size of force times the angle between the torque arm length and the size of our force. So I'm going to go with R for whatever the radius of this spinny thing is, times mg, size of that force, times the sine of theta, because I'm pretty sure this angle is the same as the angle of the ramp. All good? Any question about those choices? Excellent. And that has to equal I alpha. Here is where I made a mistake. So I'm not afraid to admit I make mistakes. I never corrected the moment of inertia. I left it as I, which is okay, actually, in the extreme. It's okay to leave it the way I did, except I didn't make it clear, as you guys are getting ready to leave, that I isn't from the center of mass. We've moved this point to the edge. So the truth is, the parallel axis theorem needs to be involved here. I just kind of said that we could drop in any value for I that we wanted, which is true, but I didn't make it clear that that might produce a more complicated result because we have to shift the moment of inertia to the edge. You guys following me? So I thought maybe we should just spend a few moments being a little bit more explicit with this answer. So here let's go. I'm going to make some of the same decisions I made yesterday. I'm going to replace alpha with A over R. I'm going to leave all the rest kind of the same, except I want to solve this for A, so I can sub it in here. And I'm kind of running out of space on this because I'm writing nice and big so the people in the back can see. So I'm going to just slide that over a little bit. And I will write one more just so we have it all down. R squared mg sine theta all divided by, and I'm going to put I parallel equals A. That all good? Did my algebra in at least a mediocre-like fashion? Alrighty. So now I think we can do the rest of this. I'm going to sub this in right over there. So mg sine theta minus friction equals, and boy, this is going to be messy, but you guys are okay with this, so let's just have it. I might move some things around, but I'll get m squared r squared g sine theta over I parallel times A. Oh, no A. Sorry, that is A. There we go. Think everything's in there. Looks like everything's there. You guys see everything there? It's icky. It's icky. Here's where I want to do a little work, if you don't mind. I parallel is actually going to be the I center of mass plus mx squared. So the x squared is r because we are shifting the axis from the center to the edge. And that's a distance r. Looks good to me, right? Does it look good to all of you? It's going to make for a complicated problem here in a minute. And you're not going to like it. It would have been actually easier to put the pivot at the center, as I found sixth period. But we're going to carry on. But you're not going to like what we're going to have to do. But that's okay. It's just algebra. And as we've discussed before, algebra is easy, right? We're all good at algebra. So I want to solve this for f. Eek. All righty. Well, I'm going to add f to both sides. But that means I got to subtract this bad boy from both sides too. So I added f to both sides, but now I'll have mg sine theta minus, m squared r squared g sine theta all over ICM plus mr squared. That's hideous. Just hideous. And I know I would love, you'd probably like this just to be done. How about we just stop right there? We are not going to. Everybody okay with what I did? Yeah.
Is that MA or is that just the acceleration?
That's MA.
Okay.
I took all of this, I put it right there, and then I just made sure we had the m squared.
Oh, gotcha. Thank you.
So, you guys are smart kids, right? What if I wanted to try and, simplify this? Do you know what the first step would be? There was a lot of talk in there. Common denominators, yeah. Common denominator is the way to go. So that, you see what we're going to have to do to have common denominators, right? Yeah. So we're going to do common denominators. I'm drawing a big line there because I'm just going to put ICM plus MR squared here. And I know I'm going to have this minus M squared R squared G sine theta. But I got to multiply all of this times this. You guys know how to get common denominators, right? So you see what I'm doing, right? Multiplying top and bottom of a fraction by the same thing. All right, so let's just give us all a little space because we're going to need it. Okie dokie. So that'll be mg sine theta times I center of mass plus mg sine theta times mr squared. Yeah, there we go. We've done it. We good? You see what we've done? Everybody okay with it all? Me too. I'd like to be just done with it all, but we're not going to be. I don't know if you see this. I see it. But do you see it? What's that? I do see the mg sine theta. I could, but if I multiplied this all out, this one right here, I have m and m. That'll make m squared, right? And I have r squared here too, right? That'll all cancel with this one, won't it? Yeah, I'm down. Are you guys okay with that? Yeah. I know you're saying, oh, Mr. Shelton, I don't care. mg sine theta times I, I'm going to put the I over there. I have reasons. Over I center mass plus mr squared equals f. All right. Now that does simplify it a lot, doesn't it? So you'd probably wonder why Mr. Shelton's going to screw with this a little bit more. But I am. I'm going to screw with it just a little bit more. And you'll understand why. I mean, you might not. I always say things like that, like you will understand why. I don't know that you actually will. It'd be nice if you did. I think some of you will understand why. But what you're probably asking yourself, am I going to be expected to have to do what you're about to do? And I'd say, I want you to. I want you to see this. I don't know if you'll be able to do it. I'm going to multiply top and bottom of this fraction by 1 over I. But why, Mr. Shelton? Why? Why, Sandy Claus? Why? Because it's a gift. Okay, so do you see what I'm doing? I'm multiplying top and bottom of my fraction by 1 over I. Now, am I okay to keep going? You're saying why, but I'm saying, look, it cancels that one out, right? And when I distribute this, I will get mg sine theta in the numerator, and I will get 1 plus mr squared divided by I in the denominator. Why would I want to do that? I'll tell you why. Isn't everything that rolls going to have an mr squared as part of its moment of inertia? So do you understand that everything in the denominator is just a number? Right? It's going to be 1 plus whatever that fraction is. That's going to be in the I, right? So if it's a solid sphere, then I get mr squared divided by 2/5 mr squared, or 5/2. If it's a hoop, it's just going to be mr squared divided by mr squared, so it'll just be 1. If it's a disk, it's mr squared divided by 1/2 mr squared, so that number's 2. Do you see why I did that? Now, yeah, we could pick a particular shape, and I told you yesterday that would be easier. And again, at the end of the day yesterday, we had I here, but that was I for the shifted moment of inertia, and I don't think we recognized what this really meant. So here's something I want you to consider. We can do this right now. Which one has more friction? The disk or the ring? Can we prove it? If we look at the ring will be mg sine theta divided by 1 plus 1, right? mr squared divided by mr squared. That is the ring. And if it's the disk, it's mg sine theta divided by 1 plus 1 over 1/2. Which, by the way, I think is 2, right? 1 divided by 1/2 is 2. So I can just cut that out and put the 2 there. We all good? So, yeah, looks like the ring is going to have more friction than the disk. Right? Proved it. Now, this came up in another class yesterday, not yours. It came up in 7th period, AP Physics 1. And a kid asked me what I think is an insightful question. The ring has more friction, but it's harder to turn. So, is that why its acceleration is less? He's trying to work out in his head why when the ring goes up the table, its acceleration is less than when the disk goes up the table. And I said, well, that makes a lot of sense. He's trying to put the pieces together about why it experiences more friction. I don't have a good way to put the pieces together in your head, but the ring experiences more friction. Why does it? Well, it's because it's harder to turn. Is that really why it experiences more friction? Well, it seems like that's the reason. Mathematically, I can prove that the ring experiences more friction than the disk. We know, though, that the ring experiences less acceleration. So though it's harder to turn, it experiences more friction, but it's still not enough for how the frictional force acts on the disk. Right? So is it because the ring is harder to turn that it experiences more friction? Or is it a result of something else that experiences more friction? I don't know if I have the answer to that completely. But I want to throw out there that you'll need to find a way in your head to put together that the disk and the ring experience different amounts of friction, even though the surfaces can be the same, the angle can be the same, and the only determining factor that is y has to be the moment of inertia. Right? It's the only thing about them. It came down to just this right here. It's the only thing about the two of them that is different. The resulting accelerations, well, they're a result of that frictional force. Now,